Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll continue with some numerical examples on torsion of shafts. Let us start with the first example. A solid shaft 60 mm diameter has to be replaced with a hollow shaft of same material with a diameter ratio 0.78 for the same torsional rigidity. Find the percentage saving in material. Now we are replacing this solid shaft by a hollow shaft for the same torsional rigidity. So we are not bothered about the torsional strength, we are only replacing it for the same torsional rigidity. We have earlier in one of the previous class we have seen that replacement of solid shaft by hollow shaft for the same torsional strength. But when you replace it for the same torsional strength, even the torsional rigidity of the replaced shaft will be greater than a solid shaft. So here we are only replacing it for torsional rigidity. So this will have less torsional strength than as a solid shaft. Now this we are replacing for the same torsional rigidity. So that means while transmitting the same torque, both shafts should undergo the same angular twist per unit length. Torque transmitted per unit angular twist per unit length should be same for both the shafts. That is the replacement for same torsional rigidity. Now the solid shaft is having 60 mm diameter. So this has to be replaced by a hollow shaft with a diameter ratio 0.78. Now the replacement is for same torsional rigidity. So when you are replacing for the same torsional rigidity, since the lengths of the shafts are same, usually the replaced shaft will have the same length because same purpose we are replacing this. So length also will be same. So assuming the lengths are same, for the same torsional rigidity, we need to only compare the J values of both the shafts. So while replacing it for the same torsional rigidity, you have to only equate the J values. If the J values are equal, both the shafts will have the same torsional rigidity. And if the lengths are also equal, a replaced shaft will have the same torsional stiffness also. Because the torsional stiffness depends on the length. Even the torsional rigidity are same. If one of the shaft is longer than the other one, that will have less torsional stiffness. So torsional stiffness depends on the length. Torsional rigidity only depends on the material property and cross section. So you have to equate J value of both the shafts for the replacement of same torsional rigidity. So you have to equate J of hollow shaft is equal to J of solid shaft, and we know that J of hollow shaft is pi by 32 into d naught to the power of 4 minus d8 to the power of 4 is equal to pi by 32 into d to the power of 4. Now d naught to the power of 4 minus d8 to the power of 4 is equal to d to the power of 4. Pi by 32 cancel. So now d naught to the power of 4 you can type outside. D naught to the power of 4 into 1 minus k to the power of 4 is equal to d to the power of 4. Now d naught to the power of 4 into 1 minus diameter ratio 0.78 to the power of 4 is equal to d is also given 60 to the power of 4. So d naught you will get 67.35, and if you multiply this with the 0.78 you will get the di 52.53. So initially the diameter was 60, the solid shaft is having diameter 60. Now you can replace it by a shaft with the outer diameter 67.35 and inner diameter 52.53. Because the diameter ratio is given as 0.78, that ratio you cannot change. So keeping that ratio constant, a hollow shaft should have a outer diameter 67.35 and inner diameter 52.53 to have the same torsional rigidity. Now the torsional rigidity will be same, that is GJ value of both the shafts will be same. because the replacement is done for same material, so it only depends on the J values. Both the shafts will now transmit the same torque while undergoing unit angular twist in unit length. So when Ts by theta by L S will be equal to G Js. So both the shafts will transmit the same torque while undergoing unit angular twist in unit length of the shaft. So we got the replacement. Now we need to find out the percentage saving in material. Percentage saving in material is Ws minus Wh, that is saving in weight divided by weight of the solid shaft into 100. Since the materials are same and lengths are same, it only depends, weight only depends on the area of cross section. So As minus Ah by As into 100. Now area of cross section of solid shaft is pi by 4 d square, and area of cross section of hollow shaft is pi by 4 into d naught square minus di square, divided by area of this solid shaft pi by 4 d square, the whole multiplied by 100. So pi by 4 you can take it outside and cancel it out. Now you get d square minus d naught square minus di square divided by d square into 100. Now you can substitute these values. We know d naught di. Substitute that, you will get the percentage saving in material as 50.65%. So much percentage of material will be saved when you replace solid shaft with a hollow shaft. Now the replaced shaft will have the same torsional rigidity, but you cannot say about the torsional strength. Torsional strength will slightly decrease, but both will have same torsional rigidity, because replacement we are asking for the same torsional rigidity, not for the torsional strength. But while replacing for the same torsional strength, the replaced shaft will have always higher torsional rigidity. Let us work out another example. A solid shaft 140 mm diameter has to be replaced with a hollow shaft of same material with a diameter ratio 0.85. Find the percentage saving in material. Here, a solid shaft with 140 mm diameter has to be replaced by a hollow shaft of same material with a diameter ratio 0.85. But here it is not specifically mentioned the replacement condition. So whether it is to be replaced for the same torsional rigidity or torsional strength is not mentioned. But whenever it's not mentioned, you should replace it for the same torsional strength. When you replace a solid shaft with a hollow shaft for the same torsional strength, the replaced shaft will have a more torsional rigidity than the solid shaft. So usually when it is not mentioned, the replacement is done for the same torsional strength, which will take care of the torsional rigidity also. Torsional rigidity or torsional stiffness of the shaft. Here we will replace the solid shaft of 140 mm with a hollow shaft having a diameter ratio 0.85. Now for the replacement, the torque transmitted by the solid shaft is polar modulus into tau max. So polar modulus for a solid shaft is pi by 16 d cube and multiplied by tau max. Now for a hollow shaft it is polar modulus into tau max. Polar modulus is pi by 16 d naught cube into 1 minus k to the power of 4 into tau max. Since the replacement is done with the same material, tau max remaining same, to have the same torque transmitted by both the shafts, you should have the same polar modulus. So polar modulus of solid shaft should be equal to polar modulus of a hollow shaft. So that is the condition for same torsional strength. So for the same torsional strength, you should equate the polar modulus of both the shafts. If it is for the same torsional rigidity, we have equated polar moment of inertia. Okay, so here we have equated the polar modulus. We know the polar modulus of hollow shaft is pi by 16 d naught cube into 1 minus k to the power of 4, and it's equal to pi by 16 d cube. Now pi by 16 cancels, d naught cube into 1 minus k to the power of 4 is equal to d cube, and we know d is given 140 mm. So you can solve for d naught. You will get the d naught as 179.06 mm, and you can multiply this d naught with the diameter ratio 0.85, which will give the internal diameter 152.2 mm. So the replaced shaft should have 179.06 mm external diameter and 152.2 mm internal diameter. If you replace with this diameters, the hollow shaft also will have the same torsional strength. While transmitting the same torque, the maximum shear stress will remain same in both the shafts. Now let us find out the percentage saving in material. Percentage saving in material is weight of solid shaft minus weight of hollow shaft divided by weight of solid shaft into 100, and weights are proportional to areas, so you can use this equation. So area of solid shaft is pi by 4 d square, area of hollow shaft is pi by 4 into d naught square minus di square divided by area of cross section of solid shaft. So you can cancel this pi by 4, okay, and you will get d square minus d naught square minus di square divided by d square into 100, and substituting for the solid shaft diameter and external diameter of the hollow shaft and internal diameter, so percentage saving you will get as 54.68. So by replacing the solid shaft by this hollow shaft with the diameter ratio 0.85, you can save 54.68% of material. That's all for today. Thank you for watching.